What's up, everybody? Mr. Dominguez here. Like I promised you guys, I was gonna post a video for you so that way you guys can see exactly how to do molar mass, grams to moles, moles to grams, and then finally grams to particle questions. So these videos are here to just kind of supplement what you guys are doing, so you guys can use them for the assignment that you guys were about to start here on Microsoft Teams. Okay. All right. So let's start off just real quick before I start. These questions are a little bit different than the questions we had in today's Zoom meeting. I changed them up just a little bit just to give you guys another example in case you guys took notes on those, and you have some more options or different types to supplement your guys' learning. So if you didn't manage to catch a Zoom lesson today, this will be a good supplement that you can use. And if you did catch a Zoom message today, this is also something that you can use as well. Okay, so let's get started. All right, so the first thing I'm going to do, right, is I'm going to figure out the molar mass of copper nitrate, right? I'm going to figure out the molar mass of copper nitrate. Now, copper nitrate is, the ratio for copper nitrate is for every one copper, there are approximately 2 nitrates. Now, nitrate is what's called a polyatomic ion, right? And it's just going to be an ion. If we were to write its oxidation number, this oxidation number for nitrate would actually be NO negative. That would be its charge as an ion. Copper, on the other hand, would be copper, but 2+. So in this situation, copper is going to be our cation, and nitrate is going to be our anion. And they're bonded together through a ionic bond, okay? Now, let's continue on. All right, so when we have copper nitrate, what we're going to do now is we're going to figure out the molar mass of it. Now, I'm going to tell you right now, right? Molar mass is a very, very, very important foundational skill that you're going to need for this class, especially because we're going to be using it quite a bit. So it's important that you understand exactly how to do it. So I gave you purposely one in which it had a polyatomic ion, and not only that, it was a polyatomic ion with more than just one of the molecules in the actual compound itself. All right, so let's take a look at this. So the first thing I'm going to do is I'm going to write down copper nitrate up here, just like that, right? And I'm going to break down every single element that's found in copper nitrate. So down here, I'm going to write copper, nitrogen, oxygen, okay? Because those are the ones that have copper, nitrogen, and oxygen. All right, now, the next thing I'm going to do is I'm going to write down how much of each I have in the molecule. So in this example, there's no coefficient, or excuse me, there's no subscript behind copper, so I know that it's only 1. So I'm going to put 1 right here, okay? Nitrogen, there's a 1 right here, but you have to notice that outside of it, there's a 2, right? And if you guys know the distributive properties of multiplication, right, you can actually move it. You would know it'd be like 2 times that and 2 times that. So realistically, what I have is 2 nitrogens in this molecule. Oxygens, because I already have 3 in the polyatomic ion itself, so I have 2 of them, it's 3 times 2. So 3 times 2 is 6. All right, so that's letting me know how much of each atom I have in the entire compound. All right, so what I'm going to do now is I'm going to multiply each of these by their molecular weight. The molecular weight of copper, according to my periodic table, is 63.55 grams. The molar, the atomic weight of nitrogen is 14.00 grams, and the molecular weight of oxygen is 16.00. Now this is using your guys' periodic table to only go up to about 4 sig figs. All right, so I'm going to multiply all these, right? And I end up getting 6 times 1, 63.55 times 1 is just 63.55 grams. 2 times 14 is just 28.00 to 4 significant figures. All right, I should be 14.01. I apologize. It should be 2 right there. I'm gonna erase this real fast. Erase. No? All right, I'll do it like this then. There we go. 28.02. And then 6 times 16 is 96.00. All right, now I'm going to add all of these up to get a grand total of 187.6 grams of copper nitrate. Now, what does this number mean? Well, what this means is that in 1 mole of copper nitrate, there are approximately, not approximately, there are 187.6 grams. So if I were to have you go get 1 mole of it, you would have to get me about 187.6 grams of copper nitrate. All right. Now, the reason I keep saying approximately, because you have to understand I'm using significant figures here and all that, but you have to understand why this is an important skill. Later on, when we get into converting grams to moles and moles to grams, having your proper or your correct molar mass, right, is crucial to making sure you get the answer correctly. Because if it's not, then you're going to get an inaccurate number. All right, so let's move on to the next example. So the next example is how many moles are found in 22.0 grams of silver nitrate. Okay, so the very first thing I'm going to do, right, because this is different. Now, this is going to be dimensional analysis, right? I'm going to be converting one thing to another thing, right? But just like I do with a lot of these problems, right, the first thing I always ask myself is I say, okay, what are they giving me and what do they want to know? Okay, so in this situation, what they're giving me is that they're telling me there's 22.0 grams of silver nitrate, and they want to know how many moles there are in that. Okay, how many moles of silver nitrate are found in 22.0 grams? So now I kind of know what I have and what I need to find out. So I'm going to write down what I have. In this case, I have 22.0 grams of silver nitrate, and I actually write it out every single time just to get in the habit of it. Okay? And what I want to find out is I want to know how many moles of silver nitrate there are. All right, so in order for me to figure this out now that I know kind of where I start to where I want to finish, what I got to figure out is what's it going to take for me to get from here to there. And the first thing I'm going to ask myself, is there a way for me to directly convert grams of silver nitrate to moles of silver nitrate, right? And the question is, yes, there actually is, right? Or the answer is, yes, there actually is. But what you have to figure out is what conversion factor we're going to use to actually solve this. Now, so far in this class, right, we've learned two different conversion factors. One of those is Avogadro's number. The second one is one that we just finished talking about, and that's molar mass, right? The molar mass, in order for us to figure out how many moles of silver nitrate there are in 22 grams, we have to use the molar mass of silver nitrate. So that's going to be our conversion factor, okay? I'll put this over 1. All right, put it over 1, multiplied, and now I'm going to use the conversion factor of molar mass. So you remember that the units for molar mass are grams per moles. Well, since we want to get rid of grams, right? Whatever's up here, right? This is grams, has to go on the opposite in the next fraction, right? If they're going to cancel each other out. So down here, I'm going to write this in red. I'm going to put grams of silver nitrate right there. Oh, I'm going to put nitrate as a no. Silver, Ag, nitrate. Our next lesson is to figure out how to actually write these bad boys down. Okay, and over the top, I'm going to put moles of silver nitrate. Now, before I even start punching in my numbers and before I start plugging stuff in, I'm going to look at my problem. I'm going to see my dimensional analysis is set up correctly, right? So I see that I have grams of silver nitrate up here, right? And then grams of silver nitrate down there. So I know that these two are going to cancel out. So if I stop my problem right now, the units that I'm left over with are moles of silver nitrate. If I look at what I want to end up with, right, I see that it actually is moles of silver nitrate. So I know that my setup is correct now, okay? As long as I understand my conversion factors, right? So for example, this one is molar mass. I'll put that down here, molar mass, right? Then I know I'm on the right path. Now that I got there and I know that I'm at where I need to be, the next thing I'm going to do is I'm going to put in the numbers that are associated with specifically with that conversion factor. So for this example, I know for every 1 mole, and by the way, it's always going to be to every 1 mole. 1 mole, right, of silver nitrate, I have approximately 169.9 grams of silver nitrate. Okay, so I'm going to multiply that across, cancel out my units, and I'm going to end up with approximately. Now, before I even start, let's just take a look at this. So I know that the number in the numerator is going to be bigger than the number in the denominator. So I know I'm going to end up with some kind of decimal. So if I end up with anything over 1, I know I'm wrong, right? So you have to make sure that you look at your problem before you even put in your calculator. So that way you know you didn't make a calculator error, okay? Now, for those that are doing this in a calculator, what I would highly recommend to you is that before you start in the calculator, right, you put this all in parentheses, right? And then you put the bottom part in parentheses as well. So you multiply everything across on the top, right, and in parentheses, then divide it by everything on the bottom, okay? And the reason I tell you this is because I'm going to tell you that, when kids, especially kids that understand how to do these problems, the biggest mistake that they make, and it's a simple mistake, is they make a calculator error. You got to make sure that you minimize your calculator errors and understand that your calculator doesn't get order of operations. Your calculator will only do what you tell it to do. right? So if you tell it, all right, multiply this, times then divide it by that, then it's literally going to do that, right? If there's a division in the middle of that, then it's going to mess everything up, right? Because much like subtraction, division does not have a distributive property. It has to be done in the correct order. So in order for you to tell it, all right, do this first before you do this, you have to put it around in parentheses. Okay, now, anyways, when I multiply and divide all this stuff through, I end up getting, put this in a different color, 0.129 to three significant figures, 0.129 moles of silver nitrate. And that's my answer right there. So what does this answer mean? Well, what this answer means is that in 22.0 grams of silver nitrate, there are approximately 0.129 moles of silver nitrate. Alrighty? Okay, so that's how you do that. Now, I'm going to give us another example, but in this example, we're going to go the other way. So instead of going from grams to moles, now we're going from moles to grams. Still the same kind of problem, just a little bit different, just tweaked a little bit differently, okay? So once again, I'm going to ask myself, I'll say, Mr. Dominguez, what information are they giving me? Well, they're giving me that I have 1.56 moles of magnesium sulfate, right? What I want to know is, what they want to know is that how many grams are found in those 1.56 moles of magnesium nitrate or sulfate. Keep saying the wrong thing. Sorry. All right, so I'm going to set up my problem. I'm going to write down what I have first. 1.56 grams, or sorry, moles of magnesium sulfate. What do I want to end up? Well, I want to end up with grams of magnesium sulfate. All right. Now, the next part of this is I ask myself, okay, in order for me to get from here, moles of magnesium sulfate, to grams of magnesium sulfate, is there any direct way in which I can do that? And the answer is yes. Once again, I have to use my conversion factors, whether it's Avogadro's number, molar ratio, or molar mass. I got to figure out which one of those I'm going to use. So the one I'm going to use for this, and what's going to bridge the gap from here to here, is going to be the molar mass of magnesium sulfate. In my dimensional analysis problem, the way for me to convert moles to grams is to, once again, use molar mass. Okay, so I'm going to write a different color. This I'm going to do it in green because it's pretty. Put my problem right there, right? And I'm going to say to myself, okay, so what are my units for molar mass? Grams to moles. I know I have to cancel out moles, right? So I'm going to put moles on bottom, down over here, moles of magnesium sulfate, and I'm going to put grams of magnesium sulfate up here. Now, once I've canceled everything out, the only unit I'm going to be left with is grams of magnesium sulfate. If I look at my final answer and I see exactly what it is, grams of magnesium sulfate, then I know I'm on the right path, because that's what I want to end up with. As long as I did my dimensional analysis wrong and I just didn't make stuff up, then I know I'm on the right path, and all I have to do now is just add in numbers, right? Let's do that right now. Okay, so remember once again that we always have just one mole, right? We got to figure out the molar mass of magnesium sulfate, which in this case is 120.4 grams. Alrighty? Okay, so once again, I'm going to multiply this through, cancel out what I have. These cancel out, and the only unit I'm left with is grams of magnesium sulfate, which is what I want. Multiply it across. When I do that, oh, yeah, okay, just making sure I did that right. When I do that, I get, let's see, 1.56 times 120.4, and I get a grand total of, use some scientific notation here, 1.88 grams, or times 10 to the second grams of magnesium sulfate. So here's my answer, and here's what it means. Now, for those that are a little bit confused, remember that 1.88 times 10 to the second is a scientific notation. Realistic, or not realistically, what it is 188 grams, okay? So what this means is that in 1.56 grams of magnesium sulfate, or excuse me, 1.56 moles of magnesium sulfate, there are 1.88 times 2 to the second power grams of magnesium sulfate. About 188 grams of magnesium sulfate found in the 1.56 moles of magnesium sulfate, okay? So that's what that means. So if I were to tell you, go get me 1.56 moles of magnesium sulfate, you would have to go to the lab and find the bottle that says magnesium sulfate, which we do have in our chem storeroom. You'd have to get me about 188 grams of this stuff and actually measure it out for me. For those that want to be my CA next year, that's one of the things that I require you guys to do. You'll have to get some of the chemicals for me and actually make them for me, right? So get good at this stuff, and then you can possibly do it, all right? As long as we're gonna have tryouts or nothing, but you know, you get the idea. Okay, so that's how much we have. All right, finally, for our last example for the day, right, is if let me use my pointer, right, how many particles are in 74.6 grams of iron oxide? In other words, rust, right? What I want to know is how many particles are there? How many atoms, how many molecules are found in 74.6 grams? The answer is not one, okay? Obviously, all right? You're going to have a lot more than that, okay? So once again, I'm going to do exactly how I did all the other problems. I'm going to ask myself a question. All right, what information are they giving me? Well, they're telling me there's 74.6 grams of this stuff. Okay, well, what do they want to know? They want to know how many particles. Okay, great. So here's what I'm going to do. I'm going to write down what I know right over here. I have 74.6 grams of this stuff, of iron oxide. Oh, that's an ugly O. Let's make that prettier. Oh, my eraser's not working. One more time. Nope, all right, screw it. It's going to look like a 6. I don't care. All right, and I want to end up, and I want to find out how many particles there are of iron oxide. This is similar to the problem I gave earlier today. Okay, so once again, this is dimensional analysis. I got to figure out how to go from here. Let's see, how to go from here to here. All right. So first thing I'm going to ask myself, is there a way for me to directly go from grams to particles? The answer is no. It's not like the other problem, right? In the other problem, there was a way for us directly to go from one step from here to here. There isn't here. There is no way. So first of all, I have to find a way, a conversion in which I can make this into this. Okay. So fortunately for us, we do have a way to do that. The first thing I'm going to do is I'm going to convert grams of iron oxide to moles of iron oxide. All right. That's the very first thing that I'm going to do. Okay, so in order for me to do that, I got to use my conversion factor. The conversion factor that I'm going to use for that is molar mass. Remember that to convert grams to moles is molar mass. All right, so the conversion factor here, I'm going to write it down here, molar mass. Okay, remember that the units for molar mass are grams to moles. Once again, grams are up here on the numerator, so I got to put it over here on the denominator to cancel it out. Grams of iron oxide up here, those moles of iron oxide. Okay, just like so. All right, so now that I've done that, if I were to stop right here, right, these two would cancel out. I would be left over with moles of iron oxide. I want to know particles of iron oxide, so I'm not done yet. However, I have to ask myself a question again. Is there a way for me to directly convert moles of iron oxide to particles of iron oxide? The answer is yes, there is, right? And it's the way that we've learned already. What we have to use right now to convert moles to particles is we have to use our other conversion factor. The other conversion factor that we got, Avogadro's number, okay? Now, what are the units for Avogadro's number? For every 1 mole we have 6.022 times 10 to the 23rd particles. So we have moles and particles. Well, I want to get rid of moles. That's going to go in my denominator. Put moles down here of iron oxide. Put particles. I'm just going to put part of iron oxide. Now, once I cancel all this stuff out, the only unit that I have left are particles of iron oxide, which is exactly what I want. So I know that my setup is now correct. Now I can go back in and punch in these numbers. Now, I'm going to say right now, this problem, the way I'm doing it right now, takes a little bit of time. Once you start getting a little bit better at this and understanding this stuff, you won't have time necessarily to do everything that I'm doing right now. But get in a habit or get used to at least setting up a problem so you know what it looks like. You'll get so good at this that you won't have to do this, right? You won't have to like remember, okay, what do I use? What do I use? Realistically, it's just like muscle memory. Your body's just going to be like, oh yeah, I know exactly what to do. You just write it down. Okay? All right, so let's go back in now and actually fill in our values. So let's go over here to molar mass. So I know that we have 1 mole, and for every 1 mole of iron oxide, we have about 159.9 grams of this stuff, right? For Avogadro's number, I know that for every 1 mole, this applies to all molecules or particles or even atoms, I have 6.02, oh, that's 0.022 times 10 to the 23rd particles of iron oxide. Okay, My problem is all set up. Now all I got to do is punch it into my calculator and see what I get. Beep, boop, beep, boop, beep, boop, right? Everything cancels out. This cancels out. This cancels out. That cancels out. That cancels out. Therefore, the only thing I have left is particles of iron oxide, which is what I want. Hooray. Now I punch it in my calculator, right? Now I will tell you that when you do this, make sure that when you type this up, that you put this whole scientific number down here in brackets. Just because what's going to end up happening is your calculator will be like, all right, it's 74.6 times 6.0022 or whatever it is, and then it'll say times 10 to the 23rd. So it'll give you some really jacked up number. The exponent has to be done first. So either put it at the very, very beginning of your sequence or wrap it in a parenthesis to make sure you get it right. So when I punch this in my calculator, I end up getting about 2.81 to 3 significant figures times 10 to the 23rd particles of iron oxide, just like that. Okay, so there's my answer. I boxed it in because I'm super, super proud of what I done, right? And I, like in chemistry, right? This isn't a math class. This is chemistry, right? So we have to ask ourselves the question, okay, what does this number mean? So what the number means is that in 74.6 grams of iron oxide, there are approximately 2.81 times 10 to the 23rd particles of iron oxide. A lot of them. Now, like I showed you in the example today, what that means, right, is if I were to have some kind of molecule, whatever the molecule is, I'm just kind of making something up right now, right? Let's pretend this is some kind of molecule. Let's pretend like this is iron oxide, even though it isn't, right? A little dumbbell here. What that means is that in 74.6 grams of this stuff, there are approximately 2.81 times 10 to the 23rd particles of this molecule. That's a lot of them, right? But anyways, so that's how you use stoichiometry to predict, not to predict, but rather how to figure out how many particles or molecules there are in any given substance. All right, guys, so that's the end of this first video. If you guys have any questions, send me a message on Remind or send me a message on Teams. All right, thanks, guys. Don't forget, hit the subscribe button, set the little bell for notifications. I don't know, I watch YouTube videos. That's what they say to always do. All right, peace out, guys. Later.